Now, we are going to talk about debugging, which is something that is generally both very important to beginning programmers and quite difficult for them. Debugging is distinct from testing. Testing is where you find that your program is not correct. Once your program has failed one or more test cases, you want to debug it. Find what exactly is going wrong and fix that problem. Finding what is wrong is its own skill set and the focus of our discussion now. Once you have figured out what is wrong, you need to return to a previous step in the 7 steps to fix the problem. You might realize that you just translated your algorithm incorrectly to code and return to step 5. Or you might realize that there is a problem with your algorithm and return to an earlier step. In some cases, you may not have generalized correctly, so you might just return to step 3 and find that you can adjust your generalization. In other cases, you may realize that the inputs on which your program is not working correctly behave very differently from what you expected. You might need to return to step 1 and work examples of such behavior to figure out how to handle those cases. Whichever step you return to, once you think you've fixed the problem, you will need to test your program again to see if the fix worked. And repeat your other test cases to make sure you did not break anything else in the changes. Before we talk about how to debug, let us take a moment to talk about how not to debug. A very common, but also very bad approach is to just try to change something and hope it works. What if I put a +1 here? Oh no, that didn't do it. Maybe -1? Imagine other situations where we are trying to find and fix a problem. Suppose you were feeling ill and went to the doctor. If the doctor said, I don't know what's wrong with you, but try this medicine and see what happens. Would you be confident in that solution? What if you took your car to the mechanic and they said, I have no idea what's wrong, but let's try replacing this part? You'd probably pick a different mechanic. Instead, you would want the doctor or mechanic to diagnose the problem and understand what is wrong before they try to fix it. The best way to diagnose the problem in both software and these other situations is with the scientific method. We hope that you have learned about the scientific method previously in your science classes and that this idea is not completely new to you. The scientific method starts with observing a phenomenon. In the case of debugging a program, this observation happens during testing. We see that the program exhibits an incorrect behavior. The next step is to ask a question. In the case of debugging, the question is almost, what is wrong and how do I fix it? The next step is to gather information and apply expert knowledge. Many descriptions of the scientific method unfortunately leave this step out and skip straight to hypothesis formation. However, leaving this step out assumes that forming a good hypothesis is easy, which is not always the case. Going back to our analogy of the doctor, if you were to describe a few symptoms, the doctor may need to gather more information, asking you about other symptoms, consulting your medical history, or checking your temperature and heart rate. Then, they apply their expert knowledge by thinking about what conditions have those symptoms and what other possibilities there are. This step is usually iterative. When the doctor sees that you are not running a fever, they may decide that there is another piece of information they want to gather. This step also gets easier the more expert knowledge you have. Eventually, you have enough information to form a hypothesis. At this point, you make a clear statement about what you think is happening. In our doctor example, the hypothesis would generally be that you have some specific disease or medical condition. In the case of debugging a program, the hypothesis would be a clear statement of what is wrong. Next, we want to test our hypothesis. The doctor may order a particular set of lab tests to confirm their diagnosis. In debugging a program, we might try a particular input and see if the behavior matches our hypothesis. One advantage we have in debugging programs is that we can examine their internal state, looking at variables in the middle of the execution via either a debugger or via print statements, which can help test a hypothesis. Sometimes, our tests show that our hypothesis was incorrect. When that happens, we return to gathering information and make use of the additional information we gain from testing our hypothesis. Other times, we accept our hypothesis. In the case of debugging a program, once we accept the hypothesis, we know what is wrong and we know what step to return to fix it. The step for gathering information is where a lot of things related to debugging education are focused. For example, many tools are useful for gathering information about what is going on in a program. Those tools help drastically in this step of the scientific method. We have also heard many instructors say things like, debugging can't be taught, you just have to try doing it. But what that really means is, Having a lot of expert knowledge makes it so much easier to form a good hypothesis. It might be really hard to do that when you don't have much expert knowledge. In fact, for some bugs, an experienced programmer may have seen a similar enough bug many times before so that as soon as they see the problem, they think they know what is wrong. As a novice, seeing this happen can make it feel like debugging is magic. But what is actually happening is that the programmer has enough expert knowledge about that particular problem that they can move through these first steps quite quickly. However, it is important to focus on these portions of the scientific method. Coming up with a good hypothesis and testing it correctly can be critical in ensuring that you are properly identifying the problem and thus actually fixing it. Before I talk about hypotheses, I want you to take a moment to think about what makes a good hypothesis and what makes a bad hypothesis.